Hi everyone, today we're going to talk about absolute age dating, which is different than relative age dating, so just pay attention. There's a little bit of math in this. To introduce the concept, I'm going to have you watch this short video.
How do we know how old something is? For people, we'd ask to see their birth certificate. For trees, we'd count the rings. But how do we know how old a fossil is? Fossils have their own internal clock. Scientists can read it by looking at the ratio of two different types of carbon atoms. Of course, every living thing is made of carbon. Plants grab carbon dioxide from the atmosphere and use it to form complex organic molecules. Animals get their carbon by eating these plants. But there's more than one form of carbon. Most carbon atoms have 6 protons and 6 neutrons. We call this carbon-12. High up in the atmosphere, sometimes cosmic rays hit nitrogen atoms. This creates carbon with 6 protons and 8 neutrons. We call this carbon-14. Carbon-12 and carbon-14 behave alike, but carbon-14 has one unique and important attribute. It's unstable. So once an animal dies, the carbon-14 in its body will start to go away. Every 5,730 years on average, about half of the carbon-14 atoms will decay into nitrogen. This is its half-life. After one half-life, the animal will have about half the amount of carbon-14 it started with. After another half-life, it will have about a quarter. And after another half-life, it will have about an eighth. By contrast, the amount of carbon-12 it has in its body will stay the same. By measuring the ratio of carbon-14 to carbon-12, we can measure how many thousands of years have passed since the animal died. Carbon dating works for fossils up to about 60,000 years old. For older fossils, scientists use unstable elements that have much longer half-lives. For Scientific American's Instant Egghead, I'm Michael Moyer.
All right, so absolute age dating versus relative age dating is how we want to differentiate these two things. Now remember, relative age dating is where we use those different principles, right? The principle of superposition, cross-cutting relation, etc., the faunal succession, all of those. So remember, we could look at the picture up here and see that our rock layer A is the oldest because of the principle of superposition, right? It's on the bottom, therefore it was deposited first. Whereas H here is going to be the youngest because it's an igneous intrusion, right? That's cross-cutting, that's that principle of cross-cutting relations. It's going across all of these, so therefore it's the youngest. So that's how relative age dating works. Absolute age dating is the numeric age of a rock layer based on these radiometric principles that they just explained in that video. So it's going to be assigned a number of years before present with a certain error factor. Okay, so that is going to be part of this, is being able to figure out within a reasonable amount of certainty how old a rock is or how old a fossil would be with this. Okay, so this radiometric dating relates to the fact that these specific elements that we use decay to a more stable element over a predicted amount of time that we're able to determine with a certain amount of certainty. Okay. Now, what type of rocks can be assigned an absolute age? Okay. Igneous rocks for sure, because we have these little mineral crystals that we're able to test, right, with certainty. So igneous rocks we're going to be able to use certain types of radiometric dating for. Sedimentary is not going to be one we're going to be able to use it for. And the reason is because sedimentary rock is made up out of other rock materials. So think about like a piece of sandstone. It may have little fragments of hundreds or thousands or millions of other rock specimens that could all be different ages. So sedimentary rock is not going to be it's not going to be useful for it. Okay, so igneous, yes, and then certain fossils, organic material, depending on the age, we're going to be able to use different ones as well. Okay, all right. Now looking at how we'll go through this process, and we'll do some practice problems here. So these unstable radioactive elements, right? They change over time into more stable ones. So we're going from the parent changing to the daughter, and we're using the concept, as he mentioned, half-life. And that's just the amount of time it takes for half of the parent to change into that daughter material. The reason we can do this is that half-life is unique and it's constant for these different elements. So it kind of is a great little marker tool we can use to be able to figure this out. Okay, so this determined in the lab with a mass spectrometer, and then after one half-life, the ratio was 50-50. So that tells us then half-life, right, you end up with a half after one half-life. Two half-lives, you just chop it in half again to a quarter, then to an eighth, then to a 16th, etc. Okay, as you keep going on and on and on. And then we're able to measure how much this is. All right, so now let's look at a sample problem here. I'm going to have you guys do some practice with these charts. The basic thing you need to understand with them, down at the bottom here is kind of a cheat sheet I've given you, and that's to look at, so for example, 50-50 is one half-life, right here. And then this is giving you that fraction as a decimal, right? So 2 half-lives, 3 half-lives, 4 half-lives, etc., based on the parent. Now up here are some of the common isotopes that we use for radiometric dating. Okay, so uranium-238 turning into lead-206. The important thing here is notice the half-life. Okay, so they're telling you the year. So carbon-14 has a half-life of almost 6,000 years. Okay, uranium, 4.5 billion years. So we're able to use that one. We're going to use these different isotopes for testing different things. Okay, so let's look at a sample problem here. A mass spectrometer analysis was used to count the number of atoms of uranium-235 and lead-207 isotopes in some zircon samples from a lava flow. The analysis revealed that 91.7 of the atoms were uranium-235, okay, and that 8.3% of them were lead-207, okay. So now to do this, all we have to do is we're trying to find the absolute age of this lava flow, okay. So what we're going to do here is look at the half-life chart, and we know that if it's, all right, well, we're talking about uranium-235, and if 91.7 of it is still the parent material, right, and then 8.3% was the daughter, that means that only, what is that, 1/8, right? 1/8 half-lives have elapsed, okay? So that's converted right here to 1/8 is 0.125. Now to figure out the age, since we know it was 1/8 of a half-life, we just have to multiply this by whatever the half-life is of uranium-235. So we look up the chart up here and see, all right, the half-life for uranium-235 is 713 million years. Okay, that's one half-life. But we just said that, right? We're not using a full half-life. We're only using an eighth, or do we say an eighth? Yeah, an eighth of a half-life, 0.125. So you just take 0.125, multiply it by whatever the half-life is, and that tells you the age of the rock material. Okay, so when we get that, that gives us what? An age of 89,125,000 years old. Okay, so that's how we're going to figure out the half-life or the age of a material by using absolute age, is figuring out how many half-lives there are, multiply that by whatever the half-life of the substance is, and that tells us the absolute age of the material. Okay? All right, if you guys have any questions, make sure you make a note of them. Contact me by email or stop me in class. Have a great day.